I want to talk about a technique that you probably have not seen before, and it's a data structure, because it's an algorithm slash data structure, and it's called suffix arrays. So to get some motivation of this algorithm, so first imagine that you have a very, very long string, and you want to repeatedly search for things inside the string. So for example, maybe you have a perfect document, and you're going to search for many different things inside this long document, right? So of course, if you're searching, if you have a long string S here and characters, and you have a bunch of patterns T1, T2 up to Tm, okay, and you want to search them, you can of course run, for example, KMP that we talked about once for every single pattern that you want to search for, and that's it. Now, if you do that, running KMP for each string, you have to call a setup to preprocess the string into a table, and basically that's the complexity is the length of the patterns. So you first have this part, which is the setup time for every single pattern that you're trying to search. And then when you're searching each pattern, it's going to take linear time in terms of the length of the string you're searching in. So it's n, but because you're doing this m times, one for each pattern is n times m. So it's more or less quadratic when it comes to the length of characters times the number of different patterns that you're searching for. Now, the thing is, because the long string that you're searching in is not changing, maybe there's a more efficient way that you can represent the string to help you, okay? And we're going to somehow try to turn this into binary search. So what are we going to do? So this concept is called suffix arrays. We're not going to worry about too much how to compute it yet, but let's just try to figure out what it is that this data structure even represents. So you have a string S, and you want to look at all the non-NP suffixes. A suffix is just a substring that ends at the last spot. Okay, so if you have a string banana, the whole string banana itself is a suffix. The last 5 characters is a suffix. The last 4, last 3, last 2 characters, and the last character. So if you have 6 characters, there are exactly 6 suffixes if you don't count the empty string. Okay? And a suffix array somehow it's a way to sort all these suffixes in alphabetical order or dictionary order, and then somehow we use this sorted suffixes to do our searches. Okay? So let's look at how this works. So again, you have the word, you start with the word banana with indices, of course, 0, 1 through 5, and the suffixes are the whole string, the last 5 letters, the last 4 letters, last 3 letters, last 2 letters, and last 1 letter. Okay, and if you were to sort them, alphabetically, what would you get? Well, A comes first, A, N, A, A, N, A, N, A, then banana, then na and nana. Okay, that's sorted. Now, why is this useful? Let's imagine that I'm trying to look for a substring. Let's say I'm trying to know if the substring NAN is in my original string. Well, a substring has to start somewhere. So in this case, it starts at index 2. So if I look at the suffix that starts at index 2, okay, NAN is a prefix of that suffix. So a substring that you're trying to look for is the same as the prefix, some prefix of a suffix. And if you look over here in our suffix array, you look down here, it is right here. It's always going to be in the first part of some element in the suffix array. All right. So let's get rid of some of these things. So now imagine that you're trying to search for, let's imagine you're trying to search for the substring A and B. We know that this doesn't exist in our normal, our original string, but let's see how we can make use of this suffix array to figure out quickly whether it exists or not. We're going to first look at the letter A, the first letter, and we're going to look at the first letter in my sorted suffix array. I can just look at the first letter, and using binary search, because the first letter is sorted, I can quickly limit what I'm searching for in this range. I can just use binary search and realize that I'm looking for A, and you look in the middle, it's B, so you know there's in first half, and then eventually you can figure out that it is the first 3 elements somewhere. Okay, so in log n time, I managed to figure out where the string could be. Second step, I look at the second element, and again, I use binary search, and this time I guess I have to be a little bit careful because there's nothing here. Okay, this is an empty spot, but as long as I'm careful with my binary search, I should be able to limit my range that I'm interested in to just these 2. Okay, so again, it is kind of log n step. Okay, and then finally, I will look at the third letter, and then I look at the third column, and then eventually I realize that no, it's not here. On the other hand, if I'm looking for A and A, then I would realize that I have 2 occurrences. Okay, and that tells me if I find this as a prefix of some suffix, it tells me that this substring A and A is present in my original string. And because I can do everything sorted, I can use binary search 1 character at a time as I move along, so this becomes quite efficient. Okay, what else do I want to say? Now, these suffixes here, you can give them a number, and the numbers simply represent where the position that the suffix starts at. Right? You don't need to know where it ends because it always goes until the very end. Okay, so the original string has ID 0. The next one, the Anana, has index 1. Nana has index 2, and so on. And in the sorted array, we can represent the sorted array not with the strings, not with the actual suffixes, but we can actually just remember the numbers. Okay. This is my suffix array. It is a representation of the suffixes that are sorted in alphabetical order. You don't want to actually store the suffixes as strings, because if you look at the length of all the strings together, it's 1 plus 2 plus 3, all the way plus 6, but in general, this is n squared, right? If you look at the size of this, this is bigger of n squared, and that's not what you want. If you look at the size of this, of course, it's just a single array, it's linear space. Okay, space. And if you have this array, then you can search relatively quickly. Now, of course, I haven't told you how to actually compare this suffix array. you could naively just say, okay, fine, I'm going to form the actual suffixes and cross sort. Okay, so if you just do the naive sort, let me just delete everything. So naive complexity is what? Well, the n suffixes, says n log n to sort, but when you do n log n sorting, it's n log n comparisons. These comparisons can be string comparisons. So in fact, when you compare two strings of length n, or close to length n, you can have another factor of n. So it's actually n square log n, which is way too long. Right? For a long string, n square is going to kill you. And it turns out that there are two ways you can do this faster. So there's a better way, which I will say a little bit about. It's n log n time. And then the best way, which is in the code library, it can actually be done in linear time. Okay? Okay, so I'm not telling you how to do that yet. So let's go back to the slides. All right, so again, if you sorted all these n suffixes, if you want to search for a prefix, you can use binary search, and the complexity is actually limited by the length, okay, of the pattern that you're searching, because we're going to look at one character at a time in the pattern, and each time you do basically binary search, right? The way that I write it is t, the length of the pattern, times log n. In fact, you can actually make an argument that it's a little bit better than that. You can say it's the maximum of log n and the length of t if you're careful. And if you search for many different strings, okay, if you're searching for many different strings, you only do this suffix array part once, and you're not going to have to worry about redoing the suffix array all over again, and you can do the binary search every time. Sorry about that. I have to pause the recording, and now I'm resuming. I think I'm still on this slide. I was talking about how if you were doing binary search, once you have managed to build your suffix array for your long string, you can search for many patterns repeatedly using binary search, and it'll be pretty quick, right? The only issue, of course, is how do you build a suffix array to begin with? And of course, if this long string that you're trying to search for ever changes, then you've got to redo everything from scratch. Okay, so how do you construct the suffix array? So again, you can't just pick all the suffixes and then call string sorting, sorting an array of strings with string comparison, because that's way too slow. So I want to kind of briefly explain to you roughly how that works. Okay, so I'm going to look at this slide, and then I'm going to kind of draw some pictures. So the idea is basically that you sort each suffix, let's say based on the first two characters. Okay, do whatever you want to sort it using, you can use a radix sort, or you can use any kind of quick sort, whatever, it doesn't really matter. Sort them, okay? Now you try to sort the suffix based on the first four characters, but the first two characters are already sorted. So you only really have to sort based on the third and fourth character, and then somehow you realize that you actually don't have to do any comparison at all for the third and fourth character, because the third and fourth characters are actually going to be the prefix of some other suffix of length 2, and you actually have already done this. Okay, so I know that this is a little bit tricky to visualize, so let me try to draw it out. So imagine that you have a bunch of strings, okay, suffix. In fact, it doesn't even, well, okay, so you have a bunch of suffix of different lengths, okay. I'll just put X's everywhere, so they can represent any letter. And we're going to sort somehow all the strings based on the first two characters. Okay, so we have already sorted them. Now we're going to try to sort based on the next two characters. So why do we have to do this? Because sometimes we might have something like C, 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 C. Oops. You might have a bunch of things that have the same first two characters, and then you're going to have to break ties if we arrange these three. Okay? So how do we sort these three entries? Well, what this looks like is actually some suffix, so it has two more characters and then a bunch more. But if you look at just this part, forget about the first two letters, remember that this is in fact a suffix of the original string. If it's a suffix in the original string, that means these three suffixes are actually sitting in the original suffix array somewhere. And more importantly, these first two letters of this suffix will be found somewhere like this, perhaps, and maybe some other one down here, right? And these first two letters will appear as the first two letters of these suffixes, which, remember, it's already sorted based on the first two letters. And so you can just read up the order in here without doing any more comparison, and immediately know how to rearrange these three. Okay, so if you've been following, what that means is that if the suffixes are sorted based on the first two characters, then you can relatively quickly figure out how to sort them based on the first four characters. And then you basically do this iteratively. Now that you know how to sort the order of the suffixes based on the first four characters, then you can double again and get the suffixes sorted based on the first 8, first 16, and so on. If you're using radix sorts at the first part, so every step, it's basically linear time to sort, right? And then they're basically log n step, so it's n log n time overall. Okay, and if you have the competitive programming book, this is the algorithm that they give you, and the code in that book makes some assumption that the period is not part of your string. Okay, if that's the case, then you have to use a different, maybe a different terminator, different illegal character to make the code work. You can also look into my code library, suffixarray.cc. It's much, much more complicated, which I'm not going to explain how it works. But you can actually strip the log n factor and in fact do this linear time. And there's no assumption on what the string can or cannot contain. Okay. Now, attached to a suffix array, there's this concept called the longest common prefix, LCP. It's a number, okay? It's a number that says between my prefix, my suffix, and the previous suffix in the sorted suffix array, how many characters are in common if I start reading from the left. Okay, so the first entry, it's always 0, it doesn't actually matter. The next entry, 1, says that between A and A, this suffix, and the previous suffix A, there's exactly one character in common if I read from the left, right, just A. Here, the next one, between A and A and A, and A and A, there are 3 characters in common. Next one, between banana and anana, there's 0 character in common starting from the left. The next one from NA and BAN, also has 0 in common. And then finally, NA and NA has 2 characters in common reading from the left. Okay, now what do these numbers tell us? If you see a number that's not 0, okay, so for example, it's 3 here, that means the first 3 letters here it's repeated at least once in this, or at least twice in the string. So this substring ANA appears at least twice. But when it's 3, shorter substrings also appear at least twice. So AN also appears at least twice. A also appears at least twice. Okay. Similarly here, the LCP value here is 2, so NA appears at least twice, and so is N. N also appears at least twice. Now here, I talked about A appearing at least twice, but in fact it actually appears 3 times. How do we know that it appears 3 times? Well, if you look at here, this range of non-zero values, 1 and 3, the minimum between 1 and 3 is 1, and it spans 2 entries. And that means that something appears 3 times. When it has 1 non-zero value, it means something appears twice. When you see something that spans 2, a consecutive chunk of 2 non-zero entries, that means something appears at least 3 times. What is this something? Well, it's we take the minimum of these numbers, which is 1, and you look at the first character, and so the letter A appears at least 3 times. In fact, it's exactly 3 times. So if you look at the suffix array code, once you have computed the suffix array, you can actually compute the LCP in linear time. Okay, and then there's routines to do that. And if you have a contiguous sequence of k non-zero LCP values, it means that there's a substring that occurs at least k plus 1 time. Right? So if you have 1 non-zero LCP value, it means that you have a substring that occurs 3 times. If you have a contiguous sequence of 5 non-zero LCP values, it means that you have a substring that occurs 6 times. And the length of the substring that occurs that many times is the minimum of all the LCP values in that range. Okay, so I want to talk a little bit about a couple of problems. Actually, I think I've skipped that because I already made videos about assignment questions. So one of them is glass beads. It's about finding the lexicographically smallest rotation. So go look at that video. Some of you that are doing some of the project questions, you might have seen a problem called shape number, which is almost the same as this. So use the same trick and you can solve it quickly. Another problem that you have to do is called Gattaca. Again, since I've already made a video about assignments questions, I'm not going to talk about it. Okay, the last one, I mean, we talked a little bit about longest common substring with dynamic programming before. And we said that we can find the longest common substring with dynamic programming, and the complexity is basically the product of the 2 lengths. Okay? But there's actually a better way of doing this using suffix array. So let me try to explain to you how that is done. So I have 2 strings now, S and T. Okay, I want to know what is the longest common substring. Now, if I just have a single string, and I want to know what is the longest repeated substring, so that's kind of a Gattaca, what that's asking. Okay, so for now, let's imagine that I want 1 string. I want the longest repeated substring. And let's say that, for example, if I have banana, the longest repeated substring is ANA, and they actually overlap, and I'm going to allow them. Okay, let's say that I allow them. If you're going to do that, all you have to do is compute the suffix array and then followed by the LCP values, and then you want to take the maximum of all the LCP values. Okay, because the maximum will tell you what is the longest substring that occurs at least twice. Right? Okay, so now we might say, okay, let's just take this S. If I'm looking for the longest common substring, let's just put S and T concatenated together. Right? So I'm making a string, a new string that has the first part S, second part T. And now I do the same thing. I run suffix array. I look at the LCP values. I look at the maximum LCP, and that will be a string. That will be a substring that occurs at least twice. Now, what can be a problem? It could be, if I just do that, it could be that the longest substring, the longest repeating substring, both occurs inside S. So that's not a common substring. It can be that both of them occurs in T, so that's not a common substring. It can also be that somehow it straddles. Okay, one of the longest common substring, repeated substring straddles, and that's also not good, right? Or there are other things that can happen. I guess straddling is the most important thing. So how do we avoid this situation? So why is that a problem? Well, for example, if S is like A, B, and T is also A, B, so in this case, actually the whole thing is the whole strings are common, the two strings are completely common. You might say that you have something like this as the longest repeated substring, right? 6 characters. But that's clearly not what you want because it's longer than either of the strings. And part of the problem is that I'm allowing things to straddle two strings, S and T. So the trick here is actually that instead of just concatenating S and T together, I'm actually going to insert a special symbol, which I'll call £, in between. So I'll concatenate 3 things together, the string S, a special symbol £, and T, and the £, this special symbol is chosen to make sure that it does not appear in either S or T. It is a special symbol that does not appear in either one. Now, if you have a common substring, you can never have 2 common substrings that straddle, okay? Because as soon as you have a substring that straddles, you cannot have something that's completely within here or completely within here as a common, because none of the characters in S or T have the hash marks, okay? And you cannot straddle like this, because the position of the hash mark will be different. So if you have common substring, it must either be one of them in S or one of them in T, but it's also possible that both of them in S or both of them are in T. So what do we do? It's actually relatively straightforward. Okay, so you compute your suffix array. So you have some suffix array, and you have an LCP array, and you proceed as normal, and you scan for the largest number. Okay, so look for the max LCP value. But when you find a number here, whatever that is, let's say 10, you're now going to look at these 2 entries, because it says that these 2 suffixes have a longest common prefix of 10. Now you have to say, does this suffix correspond to something that is in S? And does this suffix correspond to something that's in T? Okay, or vice versa, it could be T and S. How do you know that something corresponds to S? It means that the suffix will contain a £, and you can kind of work out what that is because you know how long T is, right? So if the suffix contains a hash mark, it must contain the entire T. So if you can work backwards and figure out what index in your suffix would make sure that the £, is present, right? And then if something is in T, if the suffix is only in T, there's no £, anywhere. Okay? So what? Right? So what you do is you basically look at the LCP values. For each value, you look at the number and ask, are the 2 things that are related by this LCP value one of them is in S and one of them is in P? If so, this is one possible answer. If not, if they're both in S or both in P, then you just ignore it. And out of all the possible answers, you pick the biggest one. Okay, and that will give you the maximum, the longest common substring. So how long does this take, right? If you use the linear time construction for the suffix array, then this construction is this much, right? And then scanning this LCP array can be done in linear time too. So instead of using dynamic programming and having big O of n times m complexity, in fact, it's just big O of n plus n. And that's a huge improvement. So that's all I want to say about the different things you can do with suffix arrays today.